Okay. We ended the last lecture talking about one way of systematically counting fatigue cycles, which was the rain flow counting method. And so now we will we'll apply that in a quantitative way and connect it back to cyclic stress strain diagrams in a way to kind of come full circle with a conceptual understanding of it. So I'm going to draw a more straightforward plot here. So we'll have strain just like we did before, and then some mean. Okay. So let's draw it like this. Come back to like here, to here, to here, to here, to here. Okay. So let's say that this is our strain versus time diagram. So we want to calculate how many stress cycles this is and what is the magnitude of the strain. It could be stress, it could be strain. In this case, what is the magnitude of those strain cycles? Okay. So we're going to use the rain flow counting method. So we'll start at the top. And we'll come over to this peak, and we'll go down, and we'll keep going right out to this roof level. And then we go down until we reach a negative value that's more negative than where we were before. So that's our next negative value there. So we stop that one there. And then we can go towards some of the bigger ones, right? So underneath that would start there and go down in a negative direction. And this one's going to hit multiple, eaves before it ends. All right. Oop. So that's just going to go down, and we'll just put an arrow as though, like, if there's some further stresses, it can keep going down there. Let's do a cross underneath that one now. So we'll follow from that negative valley over to here. And it goes more negative, so we're not going to keep going that time because it goes more negative than that. This is just the rules we're going to follow here. And so we can start at the next most negative location and go down this way, and then we have nothing after that. So I'll draw an arrow. Oh, it goes more negative, so it stops. My bad. Let's stop it there. Okay, so doesn't keep going. Okay. Then if we go inside of that one, we can go across, but we hit one of the other rain flows already. So we'll stop there. And we'll go inside this one on the bottom. All right, that one goes back to 0, but it could keep going. So we'll put an arrow. And then we're left with just 2 more short ones on the inside. So in the middle, kind of in the middle of the screen, we'll draw one in this section. And we'll hit that other eave. And then there's a tiny one on the top here inside. We have to go like that. And then we have to go on the top of that one. And we stop it there because it goes more positive than where we started our rain flow. So let me just make sure I got all of them on here. Yep. Okay, so far so good. The rules kind of make sense. You might be able to draw your own rain flow. Okay. So now let's count up the cycles that we have accrued. Let me go with green here. And so we'll start at the very top. And so our first rain flow counting went from the 0 position here out to where it ended. So we're going to count that as a half cycle. Okay, because we weren't coming from somewhere, it's not a full cycle. It's just a half cycle there, okay? So that's our first counting, is 1/2 cycle. I'll just draw it on the top here in green, and I'll say half, okay? And then if we go and we follow what happens next in time, so we go down in time, we reach this little section that had I'll just sort of let's see, how can I best illustrate this? I'll just put a little bracket here. Right? And so there we had one that started positive, then it went negative, then positive again, and that's a full cycle. So that's one cycle there.
Is that?
Mm-hmm.
Which one is that?
That's the little one here, this little wedge going up and down. I can highlight it's this one and this one. It's both because it's a fully reversing range. It goes fully up and down. So we count that as one cycle. So what we're looking for is those the ranges of things that go fully one way and back the other way, fully up and down. Okay, so then if we keep going, our next rain flow starts at this location and goes down all the way to the end here, right, where we have that arrow. So it spans basically the highest positive strain all the way down to the lowest compressive strain, lowest negative strain. And so it's only one direction though, right? It's not a complete back and forth. So we're going to count that as one cycle. So I'll draw it on the bottom here because it's kind of spanning the whole thing here. So that would be another cycle. Now there's a higher stress amplitude, but that's, sorry, that's a half. I don't know why I said one. That's another half cycle because it just goes one direction. So we have now gone through, and for each sort of rain flow, we're either using one path or we're using a fully reversing path. So that's how we're getting these cycles so far. So we've done that really long one. So now we can look sort of at the ones inside that long one, right? So the next one, I'll go back to green. The next one is here, and it's a fully reversing cycle. Okay. And it was interrupted, right? If you look at the decreasing strain there, it was interrupted by our other rain flow we already accounted for. So it is a perfectly matched forward and reverse strain cycle there. The same happens for the next one here. Right? It's fully reversing back and forth. And so then we've done all of our rain flows except for this last one here, which is just the half here. So we've accounted for all of the flow lines that we put in. So if we add all of these together, granted these are at different amplitudes, but we get 1, 2, 3, 4.5. I think. Yeah, so we get like 4.5 cycles of stress here. Now, we can't use this as like one block with a particular amplitude. But what we can do is we can isolate all of these cycles and then treat them all individually in sequence. So the first thing we have is the half cycle at the top. So I'll just like sort of draw some numbers of sequencing here. So if we're going to put this in like a damage accumulation model, first we have that phase at the top, right? And that has a certain amplitude to it. So that's cycle 1 at that amplitude with that mean. Then we go and we had the little one underneath that. So that would be the second damage accumulation phase. And it's one cycle at a much smaller amplitude and a high positive non-zero mean strain in this case. And then as we kept going down, we had that big half cycle, right? Our next rain flow down. So the third one is actually that longest one that I wrote on the bottom. And then we keep going down in time. Then we have this one, the kind of intermittent one, then the other intermittent one, and then finally this half cycle. So each of those phases has its own amplitude, mean, and so you can see now that this is why we need sort of automated modeling methods to account for this. And so what you would then do is using your like SNP curves and stress strain curves, and then potentially the stress strain curves for cyclic loading, right? You would have all of these as sort of your database that you were drawing from, and you would program in an algorithm to count these, to count all of these cycles, and then depending upon the amplitude and the mean stress, or mean strain in this case, you would transform that and look and find it on your data that you have in order to start doing those damage accumulation terms, right? So we would go back and we calculate how many, let's say at the first half cycle here, if I had that situation, how many cycles could I get at that, at that load level compared to the fatigue strength, and so the number of cycles at that on the SNP diagram. And then you would sum up all of the damage in order to get some damage ratio. And then you would know that a crack would initiate if that sum became greater than equal to 1. Okay? And so this is, so you can see how it might start to come together, right? And so it's not a very simple process, but it does have some detailed methods for each type, for each stage to go through and then assemble into a larger model to see if you would get fatigue or predict how many cycles you have left before you would initiate a fatigue crack. This is a strain plot. And so I'm going to go to the next slide, and I'm going to draw what a potential stress strain plot would look like for this type of loading, so that you have a better intuition on what this looks like and how it's operating. Okay. So let's go to this. And so we'll have our stress and strain on a diagram like this, like a normal stress strain diagram. So our first strain, let's assume that there's a little bit of plastic strain there. Gosh, I can't draw a straight line. So it comes up and goes like that. Okay. And so that would be the first strain level that we went to in our rain flow situation. And then after that first positive strain, it had a fully reversing strain cycle of going back to a negative value and then coming back positive again. And that's in strain. So we could say that that goes down like this, back to some low value, and then goes up further than that. So it goes back up to where it was, and then goes up further than that out to a higher strain. And then it goes into a compressive strain. And so we're going to draw that same slope down here, but instead of it stopping there, it's going to go into a compressive strain. So it's going to come down, kind of swoop down this way, like this. So this would be like if our smooth tensile specimen was undergoing this exact spectrum of loading, right? What the stress strain curve might look like. So it swoops down like that. And then we go back up to a positive strain that was kind of similar to the first little strain that we added on. So we're going to swoop all the way back up, right, to something like here. And then we go, so now we're kind of halfway through that initial rain flow diagram at the right side. And now we're going to go back to the second to last compressive strain. and it's going to go a little bit more negative than it went before. So it's going to sweep down at the same kind of slope, and it's going to reach kind of a plastic deformation mode, and it's going to come over further. And then it's going to go back positive, not all the way up to where it went, the first maximum that we had, but almost there. So it's going to sweep back up this way, same slope. It's going to come over to about here. It doesn't go all the way to that highest strain, but close. And then it's going to sweep down again and go to the most compressive strain that we had. So these curves get a little messy here and overlap, but we go all the way out, down as negative as we can, and then we go back to zero. Zero strain, not zero stress, but zero strain. So I'm going to sweep back up at the same slope, kind of our modulus, and then right over to here, back to zero strain. Yeah. So now you can kind of put together this conceptual model of, oh, I don't just have like a rain flow diagram, which is a conceptual value of strain or stress. But now you can envision it in like a tensile tester that's undergoing different levels of strain up and down in a spectrum of loading, and what is happening with the stress and strain simultaneously there. So this figure in the book was super helpful in trying to identify what's happening. And you can see now also that if we had this stress strain diagram, and this is all we had, we didn't have any ability to do the rain flow counting, the sophistication of the algorithm that we would need to count these cycles and their amplitudes and their means is just like, is wild. So if we only look at one of them, stress or strain, in this case it's a strain one, and then we plot it in sort of a rain flow fashion, we don't have to sit here and count like loops up and down. What we can do is just do the rain flow and count the cycles that way. So does that kind of make sense? Okay. So there are some sections after this talking about the last couple of requirements for, or last 3 requirements? Give me 1 second. Yeah, for the for like doing some sort of digitized model for this, and they really don't present any further information than we already know. So the last 3 steps were accounting for non-zero means, right? You just use the modified Goodman. Calculating the damage per cycle. And then adding up that damage. So those steps are unchanged. And so we'll look at a journal paper in the next lecture where they use at least some of these steps to try to put together a fatigue model and do some predictions. Okay. So this is, we're sort of jumping back and forth here, but this is the full picture for a particular concept in the book. So I just want to make sure we know where we're at in the course. So this is for, let's call it generally a stress life approach for high cycle fatigue. So we're still using these SNP diagrams. We haven't thrown those away yet. So we're still in this high cycle fatigue stress life approach. And we've had to bring in some other concepts, because when we think about cracks forming and propagating, the stress life approach doesn't handle those very well. So that's why we had to do, when we did the damage accumulation, there was that double linear rule. So we sort of said conceptually these represent these different crack growth regimes. And then we also started thinking about crack initiation, and we had to make some simplifications when it came to crack propagation. We said, yeah, cracks are going to propagate, but we're not focusing on that yet. And so that's where we are. That's where we are in the course. And we had an introduction to linear elastic fracture mechanics. And so now the last section of chapter, well, not the last section, the next section of chapter 8 applies fracture mechanics to crack propagation. And we're not just going to talk about propagation as like either not propagating or propagating to failure, because that's kind of what we had before when we had that in the extra lecture that I recorded last Friday. There was like this fatigue or failure assessment diagram. It was like, do we have ductile failure? Do we have brittle failure due to a crack? And you kind of just say, yes, a crack is going to propagate and the whole thing's going to collapse, or the crack is stable. But in real situations, there's actually stable crack growth in between there. So there's 3 stages of crack growth. I'll talk about them in more detail in a minute, but stage 1 is kind of barely detectable growth. Stage 2 is stable crack growth, and then stage 3 would be uncontrolled, very fast crack growth. So what we want to do now is put the stable crack growth into what we know about fatigue loading, so that we can put all of those things together and maybe predict how many cycles we could get, not only kind of hand waving and saying cracks are propagating, but actually using real data from experiments and measuring how fast do cracks propagate and what does that rely on. Okay, so that's where we're going next here. Okay. So I'm going to draw up an experiment of fatigue crack growth at different loads. Okay. So this is going to be on the x-axis elapsed cycles. Okay, so this specimen is a let's draw it like this. So it's sort of that Pac-Man, but it's in a rectangular prism geometry. And so it's got some notch with a crack. Sorry, I didn't draw that very well. A notch with a crack. And then it has loading that wants to open that thing in mode 1. Okay? And so now we're looking at and measuring the crack growth as some number of cycles at constant loads. Okay? So if we apply sort of a lowish load, let's say 4,000 pounds, and this is on a nickel, molybdenum, vanadium, steel alloy. Okay. We apply kind of 4,000 pounds, and the crack is going to start at 0.2 inches. Okay, so it's a known crack length at the beginning, and then this thing is just going to be cyclically loaded again and again, and the crack length as it propagates across is going to be measured. So what happens is the crack opens up, and at, let's say, 160,000 cycles, that's the upper limit of the x-axis, the crack opens up to 1.3 inches. So that's one data point up there. But the data points are not linear. It's not like it starts at 0.2 and then you just draw a straight line across this. Okay, so rather, it sort of swoops down like this. And this is figure 821 in the book, and it has data points on there, but I'm not going to draw the data points. Okay, so that would be for 4,000 pounds. Okay, so what if we apply a higher load? Let's do like 5,000 pounds. All right. So at 5,000 pounds, it doesn't last as long, so it breaks, but it still gets up to about 1.2, 1.3 inches, and it's got these 2 regimes again, like this. So that would be for what? 5,000 pounds. And so you can see where the trend is going here. The higher loads we apply, the lower the life of this sample. So the next one is going to be like 7,000 pounds, and it's over quite close, like this. And then the highest they go is like 9,900 pounds, and it's like almost vertical like this. Okay, so 9,900 and 7,000. Okay. And so we can look at this graph and we can kind of say, okay, I see some different regimes here. And the thing did not fully break, but there was a couple of like maybe 2 regimes in each one that looks like there's stable crack growth. If I look at this, I can say, okay, there's a lower slope regime and then there's a higher slope regime. And I did not write what the y-axis is, but it's crack length in inches. It's probably pretty apparent. Okay. And so we can see from this plot that if we draw like sort of what is that slope at some location, right? That would be the change in crack length dA divided by how many cycles it took to get that change dN, okay? So that's dA dN, and that's the rate of crack growth at that number of cycles, right? So this is kind of like it kind of helps you understand how fatigue affects the crack length. Everything else started at the same, like all of these started at the same condition. They did not last the same number of cycles. And then also the dA dN, that slope is not constant. So there's at least 2 regimes of crack growth on here. So from this, there were some researchers, Paris was one of them, so we'll talk about Paris law. And then in the book, the other one is Erdogan. And they said, okay, based on these types of experiments, we're going to say that dA dN is somehow related to, or I write is a function of, F parentheses, somehow related to the stress level, clearly, right? So I just wrote a sigma. It's related to the stress level because that curve changes significantly with stress, okay? The more that the crack length grows, that may also contribute to this slope, right? So we're going to put actually the crack length A in there as well. And then we'll put some geometric factors in there. We'll just call it C, right? The book calls these like higher order factors, okay? So they noticed this and they said, okay, like we sort of understand what's happening, but we don't know how to normalize this down in order to use it very well. So what they did is they looked at these factors here and they said, okay, from linear elastic fracture mechanics, we already have expressions that relate the stress and the crack length to the fracture toughness, right? So we already know that, right? So we had this expression that was like the critical fracture toughness, right, was related to like the stress times square root of pi times the crack length. Okay, so we had sort of an understanding like that. So what we're going to do is instead of looking at the slope of this crack opening rate as a function of all of these loads and things, and we're like sort of starting from scratch, we're going to use this fracture toughness as kind of an anchoring value to understand the crack propagation. Okay. So they said that it was the dA dN is a function of those things, but then they sort of changed that to be a function of the range of the fatigue strength, the fracture toughness, not fatigue strength, the fracture toughness range that the sample was seeing. And so that's what and then of course like C is still in there, right? But it's some function of that fracture toughness and C. And so that's where we come in and we get Paris law. So Paris law is very famous. And it says that DADN, rate of crack growth, is related to some type of experimental parameter, right? So we'll call it CPE, empirical parameter. And that's going to be times, there's a range of fracture toughness that's experienced to some power n. Okay. So this is what they hypothesized, and then they plotted this in such a way as it makes sense for a particular material. So I'm going to look at another plot, and this is figure 822 in the book, and it talks about the stress intensity factor, or what I like to call the fracture toughness range. Anyway, it's delta K, and if it's a mode 1, it's delta K1, right? It's in units of K psi square root inches, right? Stress times square root of length. And then they plotted that versus the DADN, right? And so you can see now that this equation here has a coefficient, the x-axis variable, right? The independent variable, delta K, and then the power law fit N. Okay. And so this was done with the same material that I wrote about before, which is that nickel, molybdenum, vanadium alloy steel. And then if this hypothesis is true, then all of the data at those different load levels from before should collapse down onto this curve. Okay. And so that's what they observed. So I'm just going to draw a bunch. I mean, you should look at this data in the book, but if we take all the different load levels and put them on here, then they do come up with generally a fit. Yes, there's some error. It's not a perfect fit to the data, but this is generally what they came up with. And so for any particular material like this nickel, molybdenum, vanadium steel, the slope of that, the slope of that line can be approximated as 3. So it's kind of like delta K to the third power. And then the empirical coefficient, that CPE, is 1.8 times 10 to the minus 19, I think. And so these units kind of get a little bit crazy here, right? So don't worry too much about the units, but it's just the coefficient so that the line fits along the y-axis there. So this would be for all of those different load levels, okay? So this is Paris law, and you can do the little Paris law like this. And so this is how people predict for some material, if they know these constants, they predict the stable regime of crack growth, right? So that is like stage 2 stable crack growth. Okay. This is also only for mode 1, okay? So this is not mode 2 or mode 3. So some of those things might change for that, right? But most of the time when we're dealing with these things, we can apply mode 1. Okay. So Paris law is most simply stated like this, but it has, you can look at this and you can see that its a rate is related to this delta K to some power. And so if you say, okay, what is A at any given time, right? If we do that, then we have to either do a summation or do an integration to get there. So we can also write Paris law like this. The crack length after some number of cycles n is equal to whatever it was before that, plus the increment that it took to get there. So we'll do it first in a summation type formulation, right? So we have some constant in here, and then delta k to the n power. Okay. So that would be one way of writing that. So this would be like if we have that discrete data from that experiment, right? And we want to know after some time, what is the crack length? If we have a more continuous way of how this might be changing with cycles, like what is this n, what is this CPE, then we can also write it in an integral form, which would be the same first two terms, but then instead of doing a summation, right, fundamental theorem of calculus, we can do an integration from 1 up to n of whatever those constants are, delta k to the n dn. Okay. This, as I mentioned, only applies to the region 2 or stage 2 crack growth. And that says in the book, it gives us a really nice range. So it says that in this region, for most engineering materials, dn is kind of 10 to the minus 3 down to 10 to the minus 6 inches per cycle. Right, so 10 to the minus 3 inch is 1/1000th of an inch, right, which is sometimes referred to as a mil in machining language. So if you have any experience with that, and then down to 10 to the minus 6 inches. So it can be, every cycle can be like, you know, in that range, and that's the stable range. The book gives a lot of thresholds for this, about like, what is the minimum delta K sensitivity at which you start to be able to use Paris law, right? What's the lowest number of cycles or lowest stress or whatever to be able to use Paris law? So they give some threshold values there. They call it like delta K threshold. And so below that value, you can't apply Paris law. And then there's also an upper limit to this where it would go into the region 3, so that's the upper limit. And that would be kind of a more subtle definition of when the crack propagates to a final failure. I don't think it's worth talking about all of those subtleties and limits on this because we're not going to use them as much for prediction. There is also some standards for this, right? So how do you do this kind of testing in order to generate those curves in order to come up with these parameters like the C, CPE, and the N, such that this can be used for prediction, right? So if you need to use this to design something that's going to be checked out by a professional engineer like a PE, and it's going to go into use, and maybe it's a vehicle or it's going to interact with people, then these standards have to be followed. And so we'll talk a little bit more about that in the next class as well. So that's kind of all I had for today. So a little bit of a second lecture that's a little bit shorter. But yeah, I'm excited about talking about sort of case studies and maybe a little bit of the standards and things like that. There's an extra lecture tomorrow. It is going to be in room 102 downstairs at 3 p.m. So if you are an on-campus student, you're welcome to attend. You don't have to. All of these lectures are posted on the class website. And that's all for today. Thanks.